The INQA conference is taking place in Tokyo in, I guess, about 6 weeks' time. And the abstract deadline is approaching very rapidly. So the abstract deadline is just, I guess, 8 days away from now. So I encourage all members of the network to submit abstracts for the conference. And it looks like we're going to have a very interesting conference. We've got a big list of, I think, about 16 or 18 invited speakers from all over the world. And it's going to be a good conference. So please do submit your abstracts. We're accepting submissions for oral and poster presentations. Good. So I shall now stop sharing my screen and ask Yuya Seki to start sharing his screen, please.
Can I see my screen?
Yes, I see your screen. I hear you very clearly. Thank you very much for joining us. Let me just briefly introduce you. So after our summer break, welcome back everyone to the regular weekly INQA seminar series. I just point out briefly that the precise scheduling has changed a bit since the summer break. So now the seminars will always be at either 9 AM UK time or 5 PM UK time, which is a change with respect from what's been happening before the summer break. Okay, so the first presentation since the summer break, I'm very pleased that Yuya Seki from Keio University will be giving the presentation, and he's going to be talking to us about quantum black box optimization by quantum annealing and machine learning. So over to you, Dr. Seki.
Okay, thank you for the kind introduction. And I'd like to thank for Professor Warburton for giving me this chance to present our recent work. And I also thanks the staffs for managing this seminar. Okay, today I'm going to talk about quantum optimization method for black box optimization problems by using quantum annealing and machine learning. And I'm Yuya Seki from Keio University, and this work is joint research with Shu Tanaka, also from the Keio University. Okay, this is the outline of my talk today. First, I'd like to introduce the background of this research to explain our motivation to study this research. Then I will introduce a quantum black box optimization method, which is called FMQA, which means a factorization machine with quantum annealing. Finally, I will introduce a couple of applications of FMQA. First, I will introduce a very simple example. Then I will explain the more complex example. And I summarize the last of my slide. Okay, let me start with the background of my research. As you know, there are a lot of combinatorial optimization problems around us. For example, in the field of manufacturing, it is required to manage computational machine time to maximize the performance of the factory and manufacturer. And in the field of logistics, it is required to minimize the cost for the delivery. And in the field of finance, portfolio optimization is combinatorial optimization problems. And in the field of advertising, it is required to optimize the schedule of advertising and target of advertising. And in the other fields, there are lots of optimization problems. In this slide, I'd like to introduce some example of combinatorial optimization problems. And here, I will introduce a very convenient websites that introduce many combinatorial optimization problems. If you're interested in this example, please visit this website. This website is developed by Fixers Amplify, which is a startup for developing applications using quantum annealing and other Ising machines. And as you can see, there are lots of combinatorial optimization problems that can be solved by Ising machines and quantum annealers. For example, traveling salesman problem is a very typical example for combinatorial optimization problems. And this example includes very industrial examples such as taxi matching problem and employee assignment problem and ride sharing. In recent research, some accelerators for combinatorial optimization problems has been developed. For example, as you know, DF systems developed quantum annealing machine based on superconducting qubits. In addition to the DF systems, Hitachi, which is a manufacturer in Japan, developed annealers based on CMOS technologies and provide a service to access their machines. And Toshiba developed the SQBM Plus, and Fujitsu developed Fujitsu digital annealer. In addition to the development of these hardwares, we are also developing a middleware to use this hardware without thinking much about the detailed information of hardwares. By using these middlewares, a programmer can access to these hardwares very easily and can develop applications by using quantum annealing and simulated annealing. And this middleware is developed by the Fixers Amplify that I mentioned before. Okay, let's move on to the very basics of combinatorial optimization problems. The first step to solve combinatorial optimization problem by using Ising machine is to formulate the cost function in this form. A cost function is a function of binary variables, and the task of combinatorial optimization problem is to minimize the cost function. And input to the cost function can be a total full space of binary variables, but in some cases there are constraints, and a definition of binary variables can be restricted. And this kind of subset is called feasible solutions. And it is known that some combinatorial optimization problems are very difficult to solve. In particular, it is believed that NP-hard problems cannot be solved efficiently by using any algorithms. But in many cases, suboptimal solution is sufficient, and exact solution is not necessary. Okay, to find the optimal solution or suboptimal solution, it is necessary to, solvers is necessary to have a mechanism to escape from the local minima. In many cases, cost function has a very rough shape like this, and there is only global minima, but there are lots of local minima around there. And to find the global minimum or local minimum, we need to escape the local minima that has a very high cost. To achieve this, meta-heuristics inspired by physical phenomena has been developed. One of that is simulated annealing. Simulated annealing uses thermal fluctuations to escape from the local minima. And SA is first proposed by Kirkpatrick in 1983. The idea is that the state can go down to the hill and not only go down to the hill, but also can go up to the hill by using thermal fluctuations. By reducing the temperature gradually, it is known that the system can converge to the global minimum. It is the convergence is guaranteed if the inverse temperature increases in a log scale given by these equations. And this convergence guarantee is proposed by Giemann in 1984. In contrast, quantum annealing uses quantum fluctuations to escape the local minimum. And quantum annealing is proposed by Kadowaki and Nishimori in 1998. And here is a result of simulation quantum annealing. Horizontal axis represents computational basis, and vertical axis represents cost of the computational basis. And cost function is represented by this blue line. This orange area represents quantum state, quantum wave functions, and the density of color represents the probability of that state. I mean the states with a high density color has a high probability to be measured. As you can see, the state at the beginning, the state has a superposition of all the possible states, and the wave function converges to the local minima like this. And it is guaranteed that the system can converge to the global minima by using these equations. These equations mean that if the total time of annealing is much greater than this right-hand side, we can get the global minima with a high probability. And this equation is given by Farhi in 2000. Okay, and there are lots of hardwares to run these algorithms. In the case of simulated annealing, we can run simulated annealing on CPU, and we can also develop a high-performance simulated annealing algorithm based on GPU. And some manufacturers made some dedicated device to run simulated annealing. And in the case of quantum annealing, DF Systems developed a dedicated device for quantum annealing and provides a web service to access their devices. Okay, in this slide, I'd like to explain some requirements for optimization with quantum annealing. In the conventional approach, by using quantum annealing machines, requires formulating the cost function in the cube form given by this equation. Cube form is a function of binary values with up to the second interaction term. C is a constant term, and Qij represents the coupling between the these two variables, binary variables xi and xj. The task here is to find the C and Qij to represent the target cost function f. But question here is that is it always possible to represent the cost function in the cube form? And the answer is no. And in particular, for the black box optimization problems, it is known that it's very difficult to find the cube form of the cost function. Okay, what is the black box optimization problems? In the black box optimization problem is defined in the computational science field, and different from the normal cost functions, we don't know the analytical form of the black box functions. But we only know the outputs of black box function for given inputs. but we cannot check all the input because it takes long computational time. So here, the task of black box optimization problem is to find the input that minimize the output of the black box function. So in the next part, I will introduce FMQA, which is a quantum black box optimization problem method to solve the black box optimization problems. Okay, before going to the detail of FMQA, I will introduce a typical approach to the black box optimization problems. One of the very basic approach is the following. As I mentioned in the previous slide, we don't know the detailed form of black box function. And in many cases, it is expensive to evaluate the black box function. So we cannot investigate all the possible inputs. A popular approach for this problem is model-based optimizations. In this model-based optimizations, black box function is approximated by another model called surrogate model. And we minimize the output of surrogate model instead of directly accessing black box functions. So in the FMQA, factorization machine is used as a surrogate model. Factorization machine has the following equations. And here, this function y is a function of binary variables x, and w0 and wi and vi vector can be are parameters. We can approximate the black box function by adjusting these parameters w0 and wi and vi vectors. Well, as you can see, this is a quadratic. So this is a kind of cube form. So we can find the optimal solutions of this function and annealing machines. The advantages of factorization machine is that the time complexity for evaluating this function is in the order of kn. The n here, n is the number of input variables, and k is the hyperparameter of this model. And k appears here, and k represents the dimension of this parameter vector vi and vj and others. And another advantage of factorization machine is that time complexity for learning is also linear as order kn. Learning here means that adjusting the parameter, these model parameters to fit the output of black box functions. Okay, this slide explains the workflow of FMQA to find the optimal solution for the black box optimization problems. First, we need to prepare the training dataset by evaluating black box functions sometimes, and we can obtain the input and corresponding outputs like this. In the next step, we train the factorization machine by using the training dataset obtained in the first step. The training can be done using backward propagation, which is a very basic approach used in the machine learning. And we can obtain the factorization machine, which represent input and output relations of black box function here. And in the third step, we try to find the likely optimal solutions by using DAB machines by minimizing the output of these factorization machines. And we obtain some output like this. Then we need to evaluate this output by using black box functions. we need to repeat this process many times, because at the beginning of this process, we have a small number of training data set. So we cannot approximate the black box function by using factorization machines. But by repeating this process, the number of training data set increases, and we can have enough number of training data set. So then we can estimate the black box function by using a factorization machine with a high performance, high accuracy. And after that, we can obtain the optimal solution for the black box function here. Okay, there are three elements in this method. First is machine learning. In the step of machine learning, we can use a GPU to accelerate calculations. And in the process to find the optimal solutions, we can use a DF machine to find the best solution, optimal solution in a very short time. Okay, this is a very simple demonstration of FMQA. In this example demonstration, I applied FMQA to find the best solution of traveling salesman problem. The task of traveling salesman problem is to find a closed path that minimize shortest closed path for the given point, like this. Here we have 8 points, and as you know, it is known that we can find the cube form this traveling salesman problem, but we try to apply FMQA to find the traveling salesman problem just for the demonstration. So this figure shows the value of coupling constant, and by using a conventional method to find the cube form of traveling salesman problem, we can get this coupling constant Qij. But we try to estimate these interactions coupling constants with the factorization machines. After calculation started, the number of training data set increases, and as the number of training data increases, factorization machine can estimate the target cube matrix with a high accuracy. After that, by sampling from these equations, by using symmetric annealing or quantum annealing, we can find the optimal solution of traveling salesman problem. Okay, I just showed a very simple example, so I'd like to introduce more complex example of FMQA. So far, we applied FMQA for various types of applications. This slide shows some example for the application of FMQA in the field of material design problems. For example, FMQA can be applied to the design of metamaterials. Here, the task is to find the metamaterials that observe or emit a specific range of wavelengths, specific range of light with wavelengths like this. And blue line represents the black body emission, and red curve represents emission by the metamaterials found by that is obtained by the FMQA. And as you can see, FMQA find the material that has a better performance. And in the case, so I'd like to introduce this design of photonic crystal laser later, because I am one of the authors of this research, and I'd like to introduce the results for the prediction of ground canonical crystal structures, because I'm an author of this research too. Okay, this slide explains the applications for the design of photonic crystal laser. The photonic crystal laser is a kind of laser with which has a very useful properties, such as we can make a very small laser, and we can make a very strong lasers. Photonic crystal lasers has a photonic crystal inside the laser, and photonic crystals has a elliptic holes and circular holes like this. And when photons comes into these photonic crystals, photon can be diffused and interfere with each other. And by adjusting the shape of these holes, we can obtain the very strong light from these photonic crystals. We collaborated with experimentalists who developed the photonic crystal lasers, and we tried the optimization of the design of photonic crystal lasers by using simulations. Here, the black box function is the simulator, and the simulator accepts the shape of these holes and returns the lasing performance Q given by here. And task is to find the best shape to maximize this lasing performance Q. Okay, here is the results. And left top figure represents best Q value for each iteration step. And red line represents the results of FMQA, and blue and green line represents a classical black box optimization method, including a generic algorithm and PSO, which is a kind of black box optimization approaches. As you can see, FMQA can find the highest lasing performance among these methods. And in addition to the high performance, FMQA can find the high value Q area compared to the other optimization techniques. To apply FMQA to the photonic crystal laser, we needed to improve the FMQA by using integer decoders. Here is a workflow of FMQA for the photonic crystal lasers. In addition to the original components such as black box function and factorization machines and annealing machines, we needed to consider the constraints filter and integer decoders. As integer decoders, we considered log encoding and one-hot encoding and domain wall encoding. The properties of encoding method is shown here. The big difference between them is the number of required bits to represent integers. In the log encoding, we only know the logarithm of the number of integers to represent all the integers. But in the case of one-hot encoding and domain wall encoding, we need to the number of integers that is comparable with the number of, we need to the number of bits to represent all the possible integers here, like this. In the case that we want to represent 4 integers, we need 4 bits in the one-hot encoding, and we need 3 bits in the one-hot encoding. The number of bits is much larger than the log encoding method. To show the performance of the extended FMQA, we first try to investigate the performance of a very simple example. In this simple example, we try to find the best structure of hydrogen molecules. The task here is to optimize the distance between 2 hydrogen atoms. And the black box function here accepts the wave function of the electrons and outputs the estimated energy given by these equations. And Hamiltonian here is given by this form, which is the second quantized Hamiltonian. We applied FMQA with the encoding method, and we obtained the following results. Here we show the result for a 3 binary encoding method, and each figure has a solid line which represents true solutions, which is actual ground state of hydrogen molecule. And we also show the result for Hartree Fock approximation by using dashed lines. And as you can see, FMQA method with encoding method can find the actual ground energies, like as shown these figures. And we also apply this method to find the prediction of the ground canonical crystal structures. In these applications, we try to find the best crystal structures for krypton and silicon and chrome CRFE and these three crystals. And this figure shows the actual obtained energy difference from the true solution versus the number of FMQA iterations. As you can see, by iterating FMQA, we can find a more optimal structures like this. And here is some results for the optimizations. We ran the FMQA 30 times, and this count means how many times we can find the ground state of that system. As you can see, for krypton, we can find the ground state 30 times, which means every time we can find the ground state of this system. But if the system becomes more complicated, sometimes we cannot find the ground state, but still we can find the ground state with a high frequency. And we also check the similarity of the data obtained by FMQA to the original training dataset. And here one means that data obtained by FMQA completely match with the actual data. As you can see, we can find that FMQA can approximate the original data with high values like this, but the system, when the system becomes complicated, the similarity decreases like this. Okay, let me summarize. First, I'd like to say that dedicated hardwares, not only the DWeb machine, but also our Ising machine, which is based on simulated annealing, has been developed to solve combinatorial optimization problems with a high efficiency. And by combining such a dedicated devices and machine learning, we can expand the range of application of simulated annealing and quantum annealing. And but we still have problems in this method. For example, we need to improve the optimization performance FMQA because sometimes FMQA cannot find the optimal solutions. For example, I mentioned in the last slide. And there is a limitation in the factorization machine itself because factorization machine has a very simple model equations. Sometimes it is difficult to estimate the data obtained by black box functions. So we need some method to improve the training performance of machine learning models. Okay, thank you very much.
Very good. Thank you very much, Yuya. That's a very interesting presentation. And I'm now happy to open it up for questions. So if anybody has a question, either raise your hand or just unmute and speak up, please. Maybe I can start with a quick question. So in your method, you essentially have, I guess, two components. You've got a machine learning component and then an optimizer. And your optimizer could be a quantum optimizer or it could be a classical optimizer.
Yes, both optimizer can be used. Yes.
Have you compared the performance of your FMQA technique using the same machine learning, but different optimizers, both quantum and classical?
Well, yes, thank you, your questions. And we compare the output for different optimizers in this research. And sorry, I don't know the reason why the difference happens, but in this case, quantum annealing has a better performance than classical optimizers for some reasons. For now, sorry, we don't know the comparison in this slide, but for now, I think the problem of classical optimizer is that classical optimizer cannot generate a wide range of solutions. I mean, the classical optimizer can provide specific solutions, but quantum annealers can provide various type of outputs. I mean, not only the optimal solutions, but also higher solutions with high energies. In the case of FMQA, using the high energy solutions, in addition to the optimal solutions, can increase training performance. So I think that's the reason why quantum annealer can provide a better performance than the classical optimizers. But sorry, I don't know the slide to explain that comparisons. But I will show that in the next paper or the second paper. Yes.
Do you think you would see a similar effect from, let us say, simulated annealing with a very large temperature? Therefore, if you constrain the simulation temperature to be high, it could also be a good optimization tool in this context.
Yes.
Okay.
Yes, you're right. That's a good approach. And now I'm trying to generate the high energy solutions by using simulated annealing with high temperatures by using parallel tempering method and other methods.
Yeah, good.
And yes, I confirm that performance can be improved.
Good. Are there any other questions for Yuya? Daniel, I see that you've turned your camera on. Do you have a question?
Yes, thank you very much. That's a really interesting talk, Professor Seki. I would actually like to contact you because I've done some work on the traveling salesman problem that might be relevant to what you're discussing. Would it be at all possible if you could provide, or maybe through Paul, provide some contact? Because I'd like to just like reach out to you after this meeting.
Sorry. Sorry, but
would it be possible to have a contact detail, a contact information, or maybe I could just put my email into the chat.
Okay.
Maybe you could reach out to me.
Sure. I mean, the great thing about the international network, it is a network which is designed to encourage collaboration. So
that's very welcome.
If Yuya would like to contact Daniel, I guess his email is in the chat.
Thank you very much. Thank you.
You're welcome.
Good. If there are no more questions, let's thank Yuya once again. Thank you very much, Yuya. A round of applause from me on behalf of the audience. And I look forward to seeing everybody at next week's seminar, which will be next Tuesday, which I guess is the 10th of September at 5 p.m. UK time. Look forward to seeing you then. Bye-bye.
Thank you very much. Goodbye.
Thank you very much.